Hi, good morning viewers. Myself Redvar Venugopal and I am Assistant Professor of Physics and I am working at Government Degree College Mahabad. Today we are going to discuss about the topic Biot Savart's law and we are also going to discuss some of its applications. Okay. So this is a topic in magnetostatics, the chapter which is in electromagnetism course, which is a syllabus for BSc Physics semester 6 students. Okay. So the learning objects of my today topic are: what is Biot Savart's law and how to use it to determine the magnetic field due to a thin straight wire, and and we are also going to learn the magnetic field created from a thin straight wire by using second right hand rule, and we are also going to determine the force acting between two current carrying conductors, and they should be parallel, and we are also going to determine the magnetic field to a circular current carrying coil. These are the things we are going to discuss today. So what is Biot Savart law? Biot Savart law is nothing but an equation. It's an equation used to calculate the magnetic field produced by a current and is known as Biot Savart's law. It's an empirical law which is named after two eminent scientists, Biot and Savart, who investigated the interaction between a straight current carrying wire and a permanent magnet. This enables us to calculate the magnitude and direction of the magnetic field which is produced by the current carrying wire. So Biot Savart's law states that at any point the magnetic field dB due to a current element dl of the current carrying wire is given by dB, that is called mu naught by 4 pi into I dl bar cross r bar divided by r square. Let me explain this. So this is the current carrying conductor. This one is a current carrying conductor. This one is a current carrying conductor, and the current flowing through that particular conductor or wire is I. Now we want to find out the magnetic field induction at point P, where dB is the magnetic field induction. So what I mean to say, we want to find out dB, the magnetic field induction at point P due to this small current carrying element dl. This dB will be depending on three parameters. It will be depending on three parameters. They are: one is, it depends on the length of the point or the distance of the point from the current carrying element. This is the current carrying element. So it depends on the distance of the point from the current carrying element. It will be, that means let us say dB is the magnetic field due to this current carrying element dl at point P. Then dB will be inversely proportional to r square. That means it inversely proportional to the distance between the point P where we want to find out the magnetic field induction due to current carrying element, and it is also proportional to sine theta, where theta is the angle between the line of joining point P and the current carrying element, that is dl, and theta is the angle between the current carrying element dl and the line of joining point P and the element, and it will be also proportional to the current itself. That means how much current is flowing through this current carrying element. It is proportional to that current. Okay. So if you combine all these things, we will come to a relation dB is proportional to ideal sin theta divided by r square. Okay. So if you put a proportionality constant, some proportionality constant, that is mu naught by 4 pi, then we can write like this, where mu naught is called as permeability of free space, and its value is 4 pi into 10 to the power minus 7 Tesla meter per ampere. Okay. Then the total magnetic field induction B at point P due to the entire current carrying conductor wire is given by B bar is equal to mu naught by 4 pi integral over the wire ideal bar cross r bar divided by r square. By using this formula, we can find out the total magnetic field at point P due to the entire current carrying conductor. Here, just remember this one. This is a unit vector. This is a unit vector in the direction of r bar vector. Okay. Now, as we have discussed, this dB is proportional to ideal sin theta by r square, or we can write dB is equal to mu naught by 4 pi. This is some proportionality constant into ideal sin theta by r square. Now the total magnetic field induction at point P due to the entire wire is given by B bar is equal to mu naught by 4 pi into ideal sin theta divided by r square. Okay. So this mu naught by 4 pi is a constant, so we can take it out. So we can write this one, B bar is equal to mu naught by 4 pi integral over the total wire and ideal sin theta divided by r square. So the intensity of the magnetic field at H, so you know already, if magnetic field induction at point P is B bar and intensity of the magnetic field H, then there is a relation between these two. That relation is B is equal to mu naught H. Therefore, H is equal to B by mu naught. This is in free space. But when you take a normal any medium, if mu is the permeability of that particular medium, then H will be B by mu. So just we have to remember this one. So the intensity of the magnetic field at P is given by H bar is equal to B bar divided by mu naught integral ideal sin theta divided by r square. So this is the Biot Savart's law in magnetostatistics. Okay. Now let us discuss about the applications part. So just observe here. Now we are going to find out the magnetic field induction at point P due to the straight current carrying wire. Okay. So consider a straight current carrying wire AB like this, and let P be a point at a distance d from the center of the current carrying conductor, and at P we need to find out the magnetic field induction B bar due to this current carrying wire. Okay. So for this one, what we are doing, we are considering a small element of that particular conductor, which is QR and of length dl bar. It is situated at distance x from the center of the wire, and it is at a distance of r from the point P. Okay. Now we want to find out the magnetic field induction dB bar at P due to this small current carrying element by using Biot Savart's law, and then we integrate between some limits. I will explain later. And by integrating this thing, we will get the magnetic field induction B bar due to this total current carrying wire at P point. So if you observe this diagram, in this diagram, this is a straight current carrying wire. This is a straight current carrying wire. The magnetic field lines are circular one. It is surrounding the wire. This is, let us say, this is the wire it is passing through this. Then the magnetic field lines are circular in shape.